expected value of this new estimate will actually be the correct value, right? So mu dash will not be an unbiased estimator. But to get the unbiased estimator, you have to multiply mu dash by 2 and subtract 1 from it. So Aniket tells me he's seeing 700 today, then my estimate should actually be not 700 but 1399. Yeah, and that will give me on average the correct estimate. So you see the point? Right? This is actually called the German tanks problem. Because actually the Allied forces use this to estimate the number of enemy tanks with the Axis forces in the Second World War. In the Second World War, right? Therefore, it's therefore called classically the German tanks problem. But you can use that as an estimator for anything. So if I want to know what is the highest number on the die, I should take the maximum that I find, multiply that by 2, and subtract 1 from it. So if I were solving this problem regularly, right, and if I use this rule to form this from my judgment, then it will then ensure that I will be correct on an average. If I just looked at 6 and said I found 6 today, so 6 must be the maximum. If I found 3 today, I must 3 is the maximum. Then I am going to significantly underestimate the quantity that I have. Right? So the idea is therefore unbiased estimators are quite important for us. And unbiased estimators are important because there are unknown quantities you want to estimate. All of us are sensible enough to say that our estimates are never exactly equal to the actual values. There is an estimation error, but we want that estimation error to be random. We don't want that estimation error to be systematic. Right? That is why we are looking for unbiased estimates. It's an estimate which is correct on an average. It's an estimate which is correct on an average. Right? And that's one of the important properties of estimators.
So this has to be done on a daily reading basis?
No, that's on a daily reading. So suppose I solve this problem only once. So Aniket does this once. And he says that for this particular problem, I found 700 taxis. So what's your unbiased estimate? My unbiased estimate will be 1399. Right? And the point is, if I did this every day, suppose I had to solve a fresh problem every day. So one day I was in Nagpur, the another day I was in Kolhapur, third day I was in Solapur. Right? And I was estimating this. Then this rule of estimating me tells me that even when my guesses are wrong, my guesses will never be systematically wrong. If I use this method of guessing, then my guesses will not be systematically wrong. Right? That's why we require unbiased estimators. Okay? That's why we require unbiased estimators. Sure? Okay, and X bar is an unbiased estimate. Now, second part of it, so that's how X bar is expectation, X bar is equal to mu. If I miss out an observation, then that never goes away, that's same. It can be made smaller by adding more observations, but it doesn't really go away. The second problem is, I have to show variance.
What was the name of the law, German tank?
It's called the German tanks problem. That's all. You can find a reference to that in a very good book called Statistical Inference by a man called Vijay Rohatgi. I think it's a very, very good book on statistical inference by Vijay Rohatgi. But it's used by pure statisticians really, but you must have a look at that. Yeah? Okay. So variance of X bar, the second thing you have to prove is variance of X bar is equal to sigma square upon n. Right? Okay, so if x1, x2, xn are independent. In general, remember, variance of x plus y, in general remember, what is the variance of z? Expectation of z minus expectation z the whole square. So think of x plus y as z. Think of x plus y as z. So this will become expected value of the whole square, because x plus y is z. Right? This can be written as, so this is A, this is B. So I can simply rewrite this now simply as x plus y Yeah? Right? Sure? I just open the brackets, no? Expectation of x plus y is expectation of x plus expectation of y. Right? So this becomes I can take expectation of x here. Yeah? Right? Okay, now please tell me what is a plus b whole square?
Yes, plus square plus 2ab.
There's something amazing about this formula. Because I met all sorts of people at whatever ages. Anything in mathematics they have learned in their lives they have forgotten. But they never forget a plus b the whole square. Everybody remembers a plus b the whole square at any point in their lives. I don't know what the reason is, but in general, otherwise everything you will forget. For example, Pythagoras theorem you will forget. Right? A plus b the whole square is okay. So using that formula, this is expectation of x minus expectation x square plus expectation of y minus expectation y square, right, plus 2ab plus 2 expectation of y minus expectation y, right? Okay? Okay? Now can you tell me what is the first part? What is this? Variance of x, right? So I will call this variance. What is this? Right? I call this variance. Plus what is this? X minus expectation x, y minus expectation y. Covariance of x and y. Right? So plus, so 2 covariance of x plus y. So we have just argued is equal to variance of x plus variance of y. Right? Explain this idea to me intuitively. What is the intuition behind this? What will be the intuition behind this? So we are looking at, see, x plus y is the sum of x and y. Right? We are looking at the variation in this sum. Now this sum consists of two components, x and y. And these components are dependent upon each other. So if x moves, y moves, and y moves, x moves. So the total movement in this sum will be the movement in x plus the movement in y that is caused by the movement in x plus the movement in y plus the movement in y that is caused by the movement in x plus the movement in x that is caused by the movement in y. So movement in x moves, so it causes some movement in y. So movement in x also causes some movement in y. So that is to be added to the movement in the system plus the movement in y, and because the movement in y causes some movement in x. Right? Okay, so suppose you have a table, okay, and say there is a surface and there is some liquid here, there is some surface, there is something which connects here. I want to look at the total movement in the liquid. I say, I have a flat surface, suppose I bang on this surface here, something moves, but something moves here as well. Then I bang something on this here, this moves, but this moves here as well. So the total movement in the surface will be, of the two surfaces together, the movement in this, plus the movement that's happened here, plus the movement in this, plus the movement that's happened here. The movement that happens because of this is the covariance. So it will be variance of x, plus the variance of y, plus the two covariance x and y. But suppose I remove this. Then what happens? The two boxes will become independent of each other. So there will be no covariance. Right? So this last part will go away. Right? So variance of x plus y is equal to variance of x plus the variance of y only if they are independent. Okay. So let me test your understanding on this. Suppose I have x plus y plus z. What will be the variance of x plus y plus z?
X and y, y and z, z and x, then
So what will be the variance of? Please put pen to paper. If you put pen to paper, then what would you do? You think of this as expectation of, minus expectation of x plus y plus z the whole square. This is equal to x minus expectation x the whole square plus y minus the expectation y the whole square plus z square, right? So you got a plus b plus c the whole square. What is a plus b plus c the whole square, friends? A square plus b square plus c square plus ab 2ab plus 2ac plus 2bc. Right? 2bc. So tell me what that sum, how will you use that sum? How will that equation? So what is the covariance?
It would be like exact same thing, the
Variance of x plus variance of y plus variance of z plus 2 covariance xz, right? Plus 2 covariance yz plus 2 covariance xy. Right? So 2 into, you can take 2 into 2 common and then covariance of xy plus etc. So all the joint terms. So we are having only 3 buckets connected together. Right? So when I move the first bucket, all the 3 buckets move. Yeah? Sure? But in general, therefore, variance of x plus y plus z is a fairly complicated summation. If I have variance of x1 plus x2 plus x3 plus xn, therefore the resultant is quite a complicated sum. Right? It could be greater than the variance of x plus y plus z or less than the variance of x plus y plus z, depending upon how the covariances go. If the covariances are negative, then the total variance will be small. If covariances are positive, total variances will be large. Right? So suppose you wanted to put together a portfolio of stocks. Okay, so x1 is one stock, x2 is another stock, x3 is third stock, x4 is the fourth stock. And you wanted to ensure that the portfolio that has as low a variance as possible. So it has a certain return, and obviously that return, the movements around that return is your risk. So if something gives you a 5% return, if you get a 0% return or a 10% return, you don't like that variation too much, right? Okay, so we'll see that we will suppose I assume that you are what we call a risk averse individual, right? What's a risk averse individual? So suppose this is some commodity X. By consuming that commodity X, you get certain utility, right? And if your utility that you get can be described like this, so every time you keep on acting more and more apples, the additional utility you get from every additional apple consumed goes down. So you get a curve like this. Suppose you are a person of that kind, right? So the more the apples you eat, the less satisfaction does an additional apple give you, right? So if I write the utility from eating apples, or the satisfaction from eating apples on this axis, law of diminishing marginal utility. But it has an interesting implication. Suppose if I give you a packet, I give you a lottery, right? Now instead of X, think of money there, right? Suppose instead of X, think of money there, right? We'll assume that richer you get, the less happiness there's an additional rupee give you. Right? Let's assume you are a person like that. You might not be a person like that, but let's assume you are a person like that. Right? So suppose this is say 10 rupees, or say this is 20 rupees. Right? And this is the utility you get from 20 rupees. say, let this be say 80 rupees. And this is the utility you get from 80 rupees. Okay? Now, suppose I give you a lottery. I offer you the two options. I say, I can give you a lottery where you can get 20 rupees with 50% probability or 80 rupees with 50% probability. So there is a box. In that box, one chit says 20 rupees, another chit says 80 rupees. You have to put your hand in, I'm going to blindfold you, and one of those chits can be drawn and you will get those many rupees. So you will get 20 rupees with 50% probability, 80 rupees with 50% probability. What is the average of that? 50? Yeah, so 10 plus 60. Right. So I have to do 20, so it's 50, right? Average. On the other hand, if I say, I'll give you 50 rupees for sure. One of your choices is this lottery, where you can get on an average 50 rupees. The other is 50 rupees for sure. Which one of the two will you take?
For sure.
You take the one for sure? If she says she'll take the one for sure, then she is this kind of a person. Why has she said that? Because look here, this is the utility of 20 rupees in hand, utility of 80 rupees in hand, this is 50, right? So utility of 50 rupees for sure is this. Whereas the satisfaction that she would get by getting either 80 rupees 50% probability or 20 rupees 50% probability will be somewhere here. In the middle of U20 and U80 and U20. Whereas the utility of 50 rupees for sure for is higher. Right? So that's because the utility function is like this. But if you had somebody who had a utility function like this, for example, then that person would say, I prefer the lottery to the 50 rupees for sure. The second kind of a person is a risk lover, whereas she is a risk averse person. She says, I might get 20 rupees or I know on an average I'm going to get 50 rupees. But this on an average 50 rupees involves the risk of downside or upside. And I don't want that risk. I would much rather have this 50 rupees in hand. Yeah? And if you are neither a risk lover nor a risk averse person, then you are indifferent. It doesn't matter, either get 50 rupees in hand or on an average 50 rupees. Sure? So in which case you would be a risk neutral person. Now typically, if she's a risk averse person, I'm a risk neutral person, then this lottery, she prefers 50 rupees in hand. So she values that lottery at less than 50 rupees. Whereas I value it at 50 rupees. So what I do is, she says I am willing to accept 45 rupees for this lottery. So I give her 45 rupees and I get the lottery worth 50 rupees. Right, so I am better off in making this transaction and she is not any worse off. Because for her at 45 rupees in hand is good enough with that lottery, right? So this transaction is actually a transaction that makes everybody better off without making anybody worse off. That is the idea behind insurance. That is, people who are risk neutral can actually insure people who are risk averse, that is, take over the risk. Because she has a utility function like this, I have a utility function like this. Yeah? Yeah, that's why, for example, if employers are risk averse, risk neutral, and employees are risk averse, then it makes sense for the employers to take all the risk. Right? So, for example, when will a franchisee arrangement be an optimal arrangement? A franchisee arrangement must be a case where the franchisee is risk neutral, right? The guy who runs the shop must be a risk neutral guy, and the franchisee owner must be a risk averse person. So CCD must be a risk averse, and the guy who's actually started the CCD outlet must be risk neutral because he's here taking all the risk. No? Only then will those arrangements be optimal arrangements. Otherwise, they'll not be optimal arrangements. Right? Okay. But so that's okay. So coming back to it, so if you create a portfolio which has 3 stocks, X, Y, Z, You can put 3 stocks in the portfolio, but you are very risk averse. So you want the portfolio to have as little risk variance as possible. You want it to give a certain return. So what kind of stocks will you choose? XYZ. You want the sum of XYZ to have as little variance as possible.
So which have no covariance.
No covariance or negative covariance. We want to minimize the variance. Huh?
Negative.
Negative covariance. So you would choose a particular stock, right? And then you would choose a second stock, which gives you a certain return, but which minimizes. You want to say that I want to create this portfolio combination, which minimizes the risk, given that it gives me a certain return. So then it becomes an optimization problem. Right? So we'll come to that. So basically, okay, so coming back again to the story that I was trying to tell you, right? So now if x1, x2, x3, x4, xn are all independent of each other, if x1, x2, x3, x4, xn are all independent of each other, then variance of x1 upon n plus x2 upon n plus x3 upon n, xn upon n. Even these very simple ideas have a lot of application in finance. So please pay attention and make sure that you are good at the derivation. You understand how the derivations are done, right? Which is equal to up to everybody understands what is, why have we been able to write this? There are no covariance terms. Why are there no covariance terms? Because x1, x2, x3, x4, x5 are all independent of each other. Right?
So what have you considered then? X1 with stocks?
No, any number. These are any random sum. Right? This is the random sum. So what is variance? So this becomes 1 upon n square because alpha variance of alpha x is alpha square variance of x. Yeah? Variance of alpha x is alpha square variance of x. Right? Sure? Now what is variance of x1? If mean of expectation x1 was mu, any particular observation can be x1. So what is the variance of x1? The same as the population variance. The same as the population variance. Right? So this becomes, 1 upon n square sigma square. This becomes n upon n square sigma square is sigma square upon n.
Sorry, variance of alpha x equals to variance of?
And variance of alpha x equals to alpha square variance of x. Because you multiply each value of a random variable by 10, then the variance gets scaled by 10 square. The variance gets scaled by 10 square, right? Okay, so variance of alpha x, right? Okay, sigma square upon n. Very important. So variance of x bar is sigma square upon n. This is very important. What is it really saying? Again, intuitively, what does it say? Look here. I got a box. In that box, there are many oranges. Okay? I want to guess the average weight of oranges in this. So what will be the average weight of oranges in this box is what I want to estimate. I have one simple way is to of course pick up one orange, weight, right? And then say that this orange seems to be 200 grams. So the average weight of oranges in the box must be 200 grams. Right? That's one way of forming an estimate. Right? I just pick up, I have a box, I want to guess what is the average weight of any given orange in this box. So I put my hand in, pick up an orange, weigh the orange. I feel it's 200 grams, so I say the average weight is 200. Now you see, this is an estimate which will be unbiased because expectation x1 will be equal to mu because any number can be x1. Right, so this estimate will be an unbiased estimate. So it's not wrong, but it can be a highly unreliable estimate. Because suppose the oranges are very widely spread. So I could have picked up another, it could have given me 350 grams. I would have picked up another orange, it could have given me 100 grams. If I keep on repeatedly doing this and doing this on an average, I will get the correct number. So the mistake that I am making is not a systematic mistake. But I am still making a mistake and the size of that mistake might be large. The fact that a large mistake gets offset, a large positive mistake gets offset by a large negative mistake doesn't really help me so much. Apart from saying that my weighing method is not systematically underestimating or overestimating. Right? So point is, each individual bit of orange that I pick up gives me information about what the actual weight is. But the reliability of this information is low because the variability of this information is very high. Right? So the variability of my guess is just the variability of the population, sigma square, because any number can be picked up in the population. No? Suppose now what I do is, I pick up one orange at random, I weigh it, I put it back, I pick up another orange at random, I weigh it, I put it back, then I